Good day, friends. Today we have with us a very special curve. A curve which is not well known, but it has a very well known property. We know a curve with that property, but not this one. Let's see what it is. We first try to understand what the property is so that we can appreciate the curve. The property is this, that for any closed curve, you take a point on the curve and we are going to define the width of the curve at that point. And we define it like this, that you take all possible chords and the length of the longest chord is supposed to be the width at this point. Now, let us take a width at this point. At this point, you may see that this will be the width, and this width may not be the same as the width at this point. The width at the 2 points could be different. But we know of a curve. That's what I was referring to, very well-known curve, a circle. And in a circle, you take any point, you know, you don't need to draw another chord. All the chords are going to be smaller and this is going to be the width at this point. The width at the other point, at any other point, will also be the diameter. In other words, at every point the width is the diameter and the diameter is constant. So here is a curve, the circle, for which at every point the width is the same, or it is a curve of constant width. We are going to have a look at another curve which is not very well known, but it does have constant width. We can't imagine that there could be anything other than circle with this property, and it is this curve. But before we go to the curve, we are going to have a look at the model. We try to understand what the constant width means in a model. Like, this is always the same. So if I put it here, and once this touches here, if I roll it, at this point it's the same width, so again it will touch, again it will touch, and so on. Because all the other chords are smaller and the width will always be the largest, and if it is the same width every time, it will always touch this. And that we know it happens in a circle. Here is another figure. It is called Roulette Triangle. It is called the Roulette Triangle, and it is a French name, French mathematician, and so the pronunciation is not very easy to make out from the spelling. Well, anyway, it is simply Rauleaux. Now, this is a roulette triangle, and a roulette triangle has this property that it will always lie between two lines. Or in other words, as we just noted, at this point all these chords are going to be smaller, but this is the largest, and that is the distance between these two parallel lines. Now you will see that it is always touching. Or in other words, at this point also, this is the width. At this point also, this is the width. At this point, this is the width. At this point, this is the width. At this point, this is the width, and so on. So you can roll it freely between these two parallel lines, which means that this curve has a constant width. Now, this is not the only one. There is another which is slightly different. As you will see, the corners have been sort of smoothened at all the three places. And this curve is also another variation of Roulette triangle, and you will see that this will also roll. And not only roll, but it will roll touching both the parallel lines. And thus, we verify that this also has constant width. Okay. There are other curves, other polygons also. We will be interested in this. Here is a pentagon which also rolls in the same way, and therefore this also has constant width. Now, we know of a curve now which is not a circle but has constant width. It's an unknown, less known curve with a very well known property, and we have two of them here, the simplest ones with us. We would like to know how to make them. In order to make them, you start with an equilateral triangle. To make the first one, we start with an equilateral triangle, and then with this, one of the vertices at the center and the length of the side as the radius, you draw an arc. Naturally it will pass from here. Similarly, with the second vertex and finally the third vertex. And now this is our Roulette triangle. Of course, the black part I am keeping here so that we know what we did. But the black part goes, and the blue one is the Roulette triangle. As you can see, this is the Roulette triangle. Okay. Now the other one, a relatively simple method, similar method. The only thing is you start with a similar equilateral triangle, but you extend the sides a little bit. So, and these two should be equal. Same length you extend at this vertex, and the same length you extend at this vertex. And now, as before, as we did here, we take this vertex, first vertex, and this small extended radius, and draw an arc. Same thing with this vertex and extended radius, extended side. And third one also. And now, again, second round with the same vertex and this length, whole length. If we call this A and this length B, extended length B, and the length of the side is A, then this is also B. So this is A plus B. You take this as center, one vertex, A plus B as radius. This is also A plus B, so it will pass through this. Similarly with this as vertex and A plus B radius, and third thing here. And now you will see that this is our Roulette triangle. Now, so we know how to make the Roulette triangle also, and we also can make, if we want to, some more Roulette polygons. But here is an introduction to a relatively known curve. Thank you.